Machines once existed that ran on sound, sunlight, and even the simple heat of a cup of coffee. These are the secret histories of non-traditional engine designs lost to time, real inventions that challenged everything we thought we knew about power. By the end of this journey, you will see the entire story of human innovation in a new light, uncovering a hidden lineage of mechanical genius. We will investigate why a nearly silent engine from the 1800s was too elegant to survive, and how a jet-powered family car from the 1960s became a forgotten dream. This is more than a history lesson. It is a recovery of forgotten futures. What forgotten idea from the past do you think could change our future the most? The world we live in runs on a single, dominant idea of power. It is a world of pistons pumping, cylinders firing, and fuel burning in a cycle so universal we rarely stop to question it. But before this single vision solidified, the landscape of mechanical invention was a spectacular chaos of possibility. This was the dawn of difference, a time when what constituted an engine was still up for debate. Non-traditional propulsion is not just a different way to build a motor, it is a fundamentally different way of seeing energy itself. These are machines that step completely outside the paradigm of the internal combustion engine, rejecting the very principles of pistons and controlled explosions that we take for granted. They are the roads not taken, the answers to questions we have forgotten how to ask. Consider an engine that has no moving parts at all, humming silently as it turns heat directly into electricity. Picture a device powered by nothing more than the temperature difference between a warm cup of coffee and the cool air of the room. Some even ventured into realms that sound like science fiction, exploring how collapsing bubbles of light or the subtle pressures of empty space could be harnessed for work. These are not just engineering curiosities, they are philosophical statements carved in metal and glass. They force us to reconsider our relationship with the universe, asking if power must always be loud, violent, and wasteful. The secret histories of these creations are not locked away in classified files. Their obscurity is far more mundane and perhaps more tragic. They were buried by the sheer economic momentum of the oil age, deemed unprofitable next to a world standardizing on gasoline. Some were simply too elegant, too quiet for a noisy industrial era. Others were visions so advanced that the materials or mathematics to perfect them did not yet exist. To understand this lost diversity is to grasp the true scale of what was left behind, a hidden continent of technological thought we are only now beginning to rediscover. Robert Stirling's vision in 1816 was an engine that shunned violence. His creation required no internal explosions. Instead, it harnessed the gentle, ceaseless dance of a trapped gas, heated and cooled in an endless cycle. Imagine a sealed chamber of air. Apply heat from any source, even a small candle, to one end. The air inside expands, pushing a piston. Move that expanded air to a cool area, and it contracts, pulling the piston back. This simple, rhythmic expansion and contraction is the heart of the Stirling engine, a machine of profound quiet and cleanliness. It was an external combustion engine, meaning its fire was separate, a quiet servant to the elegant physics within. This separation meant it could run on anything that provided a temperature difference, from burning coal to the focused heat of the sun. Its potential for near-silent operation and theoretical efficiency was staggering. So why did such a brilliant concept fade into obscurity? The answer lies in the temper of the industrial age. The 19th century was a time of immediacy, of raw power and rapid starts. Factories and locomotives demanded force, delivered now. The Stirling Engine was a thoughtful scholar in a barroom brawl. It took time to warm up, and for its weight, it could not match the explosive, instant power of steam or the new internal combustion engines. It was too graceful, too patient for a world in a hurry. Its downfall was not a failure of principle, but a misalignment with the era's hunger. Yet the story does not end there. The very qualities that made it unsuitable for the factory floor became priceless in other, more secretive realms, where absolute silence was a matter of life and death. Like in advanced military submarines gliding silently through the deep, the Stirling Engine found a home. Its reliability and quiet made it perfect for powering systems without giving away a vessel's position. Even NASA looked to this old idea for new frontiers, using Stirling designs in space probes where dependable, long-term power from radioactive decay, heat, or sunlight was essential. The Stirling Engine never died. It simply went underground, a ghost of an idea that refused to be forgotten, waiting patiently for a world ready to listen to its quiet hum. While the Stirling Engine was a quiet scholar, the 1960s roared with a completely different kind of rebel. A new star blazed in the automotive sky, promising to tear up the rulebook on engine design. This was the Wankel Rotary engine, a machine that replaced the familiar up and down dance of pistons with a single, spinning triangular rotor. This rotor pirouetted inside a uniquely shaped chamber, a figure called an epitrochoid, generating power in a smooth, continuous whirl. The result was an engineering marvel, compact and incredibly lightweight. It delivered high power with breathtakingly few moving parts, and it ran with a silky smoothness that piston engines could never match. Companies like Germany's NSU and Japan's Mazda championed this revolution, putting these compact powerhouses into sleek sports cars that promised a smoother, higher revving future. For a moment, it seemed the internal combustion engine as we knew it was about to be dethroned. But the Wankel's brilliant design held a hidden curse. Its very geometry created inherent challenges with sealing. The tips of the spinning rotor, known as apex seals, scraped against the chamber walls at tremendous speed. Keeping these fragile seals intact was a constant battle. They wore out quickly, leading to high oil consumption and unburned fuel slipping past, which meant problematic exhaust emissions. For a time, its raw performance seemed to outweigh these flaws. Then the 1970s arrived, bringing with them a wave of stringent environmental regulations, a new social conscience focused on clean air. This was the iceberg that sank the Wankel's technological Titanic. Its fundamental design made it nearly impossible to meet the new standards for fuel economy and emissions without a complete, and likely impossible, redesign. The brilliant revolution burned out almost as fast as it had ignited, leaving behind a haunting legacy of what if for engineers and car enthusiasts the world over. It was a stark lesson that a brilliant idea is not always a practical one, and that the march of progress is sometimes dictated not by engineering genius, but by the demands of the world that engine must live in. While the Wankel stumbled on emissions, another American giant was placing an even more spectacular bet. Chrysler did not just build a prototype, it launched a social experiment, handing the keys to a jet-powered future to ordinary families. For 2 years, from 1963 to 64, 50 lucky households became test pilots for the Chrysler Turbine car, a vehicle that looked like it had flown in from another decade, with its sleek Italian bodywork by Gear. The heart of this machine was a gas turbine engine, a close relative of the powerful jet engines propelling aircraft across the sky. Its operation was a study in elegant simplicity, with far fewer moving parts than a piston engine. It ran with an almost vibration-free smoothness, producing a distinct, futuristic whine instead of a rumble. The engine was also a marvel of fuel versatility, capable of running on practically anything combustible, from conventional diesel and kerosene to unconventional sources like peanut oil, soybean oil, and even certain types of perfume. The freedom from a single fuel source was intoxicating, a vision of true energy independence. But this beautiful dream had concrete problems. The turbine engine suffered from a noticeable throttle lag, a dangerous delay between pressing the accelerator and the car actually surging forward, a major flaw in busy traffic. It was also notoriously thirsty at low speeds and idle, gulping down fuel while sitting at a stoplight. Its most dramatic flaw, however, was the heat. The exhaust gases shot out at temperatures so incredibly high they were known to discolor and even melt the asphalt on the street behind it. Chrysler's breathtaking gamble proved that the technology worked, but it also revealed a harsh truth. The gas turbine was a creature of the open highway, born for constant, high-speed flight. It was fundamentally ill-suited to the stop-and-go reality of daily commuting. The future it promised was one of simplicity and smoothness, but it was a future that demanded we change our driving behavior and our entire infrastructure, a price the world was not ready to pay. This was not a failure of engineering, but a collision between a brilliant machine and the inconvenient realities of human life. That distinct, terrifying buzz was the sound of pure physics weaponized. During the Second World War, the German V-1 flying bomb, or doodlebug, introduced the world to the pulse jet engine, a device of terrifying simplicity. Unlike the complex turbines or precise pistons of other engines, the pulse jet had almost no moving parts at all. Its core was just an empty tube with a set of shutters at the front. Fuel was injected into this tube and ignited. The explosion forced the shutters closed, blasting exhaust gases out the back to create a pulse of thrust. This then created a vacuum that sucked the shutters open again, pulling in fresh air to mix with more fuel, starting the cycle anew. This happened not smoothly, but 50 times per second, creating that unmistakable, jarring buzz that struck fear into those below. It was a brute force engine, cheap to stamp out by the thousands, a product of martial necessity where simplicity and cost trumped all other concerns. Yet that very simplicity was a cage. The violent, resonant pulses made the engine wildly inefficient, gulping fuel at an alarming rate. The noise was physically punishing, and the vibrations shook the airframe apart with relentless force. It was a technological dead end, an engine whose only purpose was to be a disposable delivery system for a single, one-way journey. The pulse jet stands as a stark monument to a different kind of innovation, one born from the urgency of conflict. Its story is a chilling reminder that elegance in engineering does not always lead to a peaceful future. Its haunting buzz echoes not as a promise, but as a warning from a past where the simplest ideas could be harnessed for the most destructive ends. Even the air around us could be made to work. Before the roar of high-pressure steam defined an age, the first true engines whispered into existence, powered not by fire's fury, but by the silent, crushing weight of the atmosphere itself. These were the atmospheric engines, machines that mastered the void. They worked on a principle of profound simplicity. Imagine a large piston inside a cylinder. Steam is introduced below it, not to push it up with great force, but simply to fill the space. Then, cold water is injected, causing the steam to instantly condense back into water. This rapid condensation creates a partial vacuum beneath the piston, with the pressure below suddenly vanishing. The relentless weight of the Earth's entire atmosphere above, 14 pounds on every square inch, slams the piston down with immense force. That powerful downward stroke was the work used to pump water or turn machinery. This was the flame liquor principle in action, a slow, rhythmic, and incredibly reliable process. For decades, these gentle giants were the quiet workhorses of mines and early factories, their massive beams rising and falling with a patient, predictable grace. They were foundational, teaching humanity its first real lessons in harnessing heat to create motion. Yet their quiet strength contained a fundamental limit. They were slaves to atmospheric pressure. Their power was capped by the very air we breathe. The revolution came with a dangerous new idea: high-pressure steam. Why wait for the atmosphere to push a piston down when you could use concentrated steam to blast it up and down with far greater speed and force? The high-pressure engine was a screaming thoroughbred next to a patient plow horse. It was smaller, more powerful, and perfectly suited for the new age of locomotives and fast-moving machinery. The atmospheric engine was rendered obsolete, a technological ancestor we quickly outgrew. But its ghost never left us. That core idea of harnessing a vacuum, of making power from emptiness, echoes through time. It is the same principle that allows a simple drinking straw to function, and it reappears in the most advanced scientific instruments. The atmospheric engine's legacy is a philosophical one, a reminder that sometimes the most powerful force is not what we add, but what we take away. Fire could become the piston itself. This was the breathtaking promise of the orbital combustion process engine, a design that discarded solid metal parts in favor of a self-contained ring of flame. Picture a donut-shaped cylinder, a continuous circular chamber with no beginning and no end. Instead of a metal slug moving up and down, this engine injected a precise mixture of fuel and air, then ignited it to create a single, rotating fireball. This burning vortex became the piston, a toroidal wave of pressure that spun around the chamber, compressing the fresh charge ahead of it and pushing the exhaust out behind. It was an engine built from pure energy, a concept that promised to burn fuel so completely and so lean that emissions would plummet and efficiency would soar. By controlling the very propagation of the flame itself, the orbital combustion process aimed to solve the core inefficiencies that had plagued internal combustion for a century. Yet, taming this beautiful idea was a battle against physics itself. Containing and stabilizing a self-sustaining ring of fire under the brutal pressures and temperatures of a working engine required an unprecedented level of control. The system needed perfectly timed fuel injection and ignition, a delicate dance that had to be maintained thousands of times per minute. The slightest instability would cause the flame to falter or become erratic, destroying the delicate process. The materials sealing this chamber of controlled chaos were pushed to their absolute limits, struggling to contain the very heart of the sun. The orbital combustion process engine remains a monument to a radically different way of thinking, a brilliant answer to a question few dared to ask. It was not a failure of vision, but a testament to the immense challenge of commanding a fundamental force of nature. Its story forces us to wonder if some ideas are simply too perfect, too pure, for the imperfect world of metal and manufacturing. Sound itself can become a piston. In the quietest corners of physics, one of the most ethereal of lost designs harnesses the raw power of a standing wave. Thermoacoustic engines perform a kind of mechanical sorcery, using intense, high-amplitude sound waves trapped within a pressurized gas to achieve what seems impossible. They force heat to travel against its natural flow, pumping thermal energy from a cold area to a hot one, and in doing so, they generate usable mechanical work. The core of the machine is breathtakingly simple, often just a sealed tube, a heat source, and a heat sink. There are no turbines, no pistons, no gears, no moving parts at all except for the sound wave itself, a resonant, pulsing column of air that acts as the engine's only moving component. This profound minimalism is its greatest strength, promising almost limitless reliability. A machine with no parts to wear out could, in theory, run for centuries. Imagine an engine powered by the diffuse warmth of industrial waste heat, or by the focused rays of the sun, humming along silently for generations without ever needing a single repair. This is not science fiction, it is a forgotten branch of physics made real. Its history is a secret whispered in advanced laboratories, a technology that feels like it defies the very logic it is built upon. Why did such an elegant concept not transform our world? The challenge lies in the subtlety of its power. While incredibly efficient at moving heat, translating that precise acoustic energy into a strong, concentrated mechanical force for tasks like turning a wheel or a generator proved difficult. The engine was a master of a very specific, delicate kind of work, out of step with an industrial world that demanded raw, brute force. Yet, this very quality makes it a holy grail for frontiers where no mechanic will ever travel. For deep space probes on missions lasting thousands of years, or for power systems on the far side of the moon, a thermoacoustic engine represents a perfect, eternal power source. It is the ultimate expression of a machine built not from metal, but from an idea, a ghost of sound doing the work of an engine, waiting for a future quiet enough to hear its potential. The silent hum of a thermoacoustic engine is one kind of ghost, but what about a machine that generates power with no moving parts at all? This was the radical promise of MagnetoHydrodynamic Generation, or MHD. Imagine a jet of superheated gas, so hot it has become a shimmering, electrically conductive plasma. Now fire this plasma through a channel surrounded by immense magnets. As the charged particles cut through the magnetic field, a fundamental law of physics takes over, inducing a powerful electrical current directly across the flow. No spinning turbines, no whirring generators, no mechanical middlemen. Electricity is born in a single, silent, motionless step from the raw motion of fire itself. During the 1960s, this was not just a laboratory curiosity. It was seen as the inevitable future of high-efficiency power. The theoretical potential was staggering, promising to leapfrog the fundamental limits of every rotating machine that had come before. But the secret history of MHD is a chronicle of a dream buried under mountains of impossibility. The first hurdle was temperature. To create that conductive plasma, you needed to heat a gas to temperatures rivaling the surface of the sun, far beyond what any conventional furnace could produce. Then came the magnets, requiring fields of such immense strength they demanded colossal amounts of energy just to maintain. And finally, there was the plasma itself, a screaming, corrosive torrent that would eat through most known materials like acid through paper. Finding a substance that could line the channel and survive this hellish environment for more than a few hours was a challenge that ultimately proved too great. This forgotten path represents the ultimate dream of direct energy conversion, a machine that is all heart and no body. It remains a tantalizing vision of pure physics harnessed for work, a silent engine that we could see but never quite hold. That promise of a perfect, vibrationless engine found its most passionate champion in the 1920s. Russell Burke was not just an inventor, he was an evangelist for a mechanical revelation. His engine was a declaration of war against complexity itself. It tore up the conventional engine blueprint and started over with an almost philosophical purity. At its heart was the Scotch yoke, a mechanism that replaced the familiar connecting rod and crankshaft. This elegant swap converted the piston's linear motion into rotation with far less friction and a beautifully balanced sinusoidal movement. The design used two pistons opposed in a single cylinder, their heads facing each other across a shared combustion chamber. As they moved inward together, they compressed the fuel-air mixture between them. Upon ignition, the explosion forced them apart, their motion captured by the Scotch yoke to spin the crankshaft. This two-stroke, opposed piston design promised a mechanical symphony. Its proponents swore it ran with an otherworldly smoothness, producing virtually no vibration. They claimed its efficient scavenging of exhaust gases led to astoundingly clean combustion, with almost no unburned fuel to pollute the air. Most tantalizing of all was its reported fuel flexibility, able to run happily on gasoline, diesel, kerosene, or even alcohol with minimal adjustment. It sounded less like an engine and more like a mechanical utopia. So what happened to this miracle? The story immediately plunges into shadow. The secret history of the Burke engine is a battleground of competing narratives. One persistent legend claims the design was deliberately suppressed. The story goes that major oil and automotive corporations, threatened by an engine that promised incredible fuel economy and could run on virtually anything, acquired the patents only to bury them forever, protecting their lucrative empires. It is a compelling tale of David versus Goliath, of a brilliant outsider crushed by corporate greed. Yet another, more sobering analysis points not to conspiracy, but to the engine's own internal demons. Critics and engineers who have studied the design point to the immense mechanical stresses placed on the Scotch yoke components. The very simplicity of the system may have created points of extreme pressure, leading to potential failures under continuous high load. The scavenging process, while elegant in theory, might have been difficult to perfect in practice, leading to inconsistencies. Was the Burke engine a flawless masterpiece murdered in its crib? Or was it a beautifully flawed concept that could never quite live up to its own breathtaking promises? The truth is likely lost to time, a murky blend of both. The Burke engine survives today not on our roads but as a cult legend. It is a ghost that haunts the garages and workshops of amateur engineers and dreamers who continue to build and test their own versions, chasing that phantom of perfection. Its story is a cautionary tale about the fine line between visionary genius and impractical obsession. It forces us to ask a difficult question. When a revolutionary idea fails, is it because the world was not ready, or because the idea itself was just a beautiful, unworkable dream? Starlight itself can push a spacecraft. This is the radical promise of the solar thermal rocket, a design that treats the sun as its only fuel tank. Forget burning chemicals or splitting atoms. This engine runs on pure, concentrated sunlight. Imagine a giant mirror, a parabolic dish focusing the sun's rays into an intense point of heat inside a chamber. Liquid hydrogen, colder than the void of space, is pumped through this solar furnace. In an instant, it is heated not by a flame, but by light, transforming into a superheated gas screaming for release. This expanding plasma is then funneled through a traditional rocket nozzle, creating thrust with an elegant simplicity that chemical rockets cannot match. The efficiency is staggering because every bit of propellant is used for momentum, not burned as fuel. It is a silent, clean, and potentially endless engine for sailing between worlds. Its blueprints were drawn in the 1970s and 80s, a serious contender for interplanetary missions in the preliminary studies of NASA and other space agencies. It was the logical next step, a sustainable path to the stars, but that future was sidetracked. The political and engineering focus of the space race shifted decisively toward the raw power of chemical rockets and the dense energy of nuclear thermal propulsion. The solar thermal rocket was a gentle sailboat in an era that prioritized explosive speed. It was deemed too slow to start, requiring time to position its mirrors and heat its core, and its power was intrinsically linked to its distance from the Sun, weakening as it traveled to the outer planets. So the concept was filed away, a beautiful solution waiting for a problem we had not yet fully embraced. It stands as a monument to a different kind of space age, one not of explosive force but of patient, intelligent harvesting of the energy that already floods the cosmos. Its day in the sun may yet come, when we finally decide that the best way to explore the heavens is to ride the light that already fills them. Before the roar of the modern diesel engine became the soundtrack of industry, a slower, tougher, and far more forgiving machine held sway. It was the hot bulb engine, a semi-diesel workhorse that demanded patience and rewarded it with unbreakable loyalty. To start one of these giants was a ritual. You would first take a blowtorch to a small, externally mounted metal chamber, the hot bulb itself, heating it until it glowed a cherry red. Once the bulb was searing hot, you would manually turn the massive flywheel. As the engine lumbered into motion, it would draw a fine spray of fuel oil into the superheated bulb. This fuel would not explode from compression alone, as in a true diesel, but would instead ignite on contact with the scorching metal surface, a process called surface ignition. The engine would chug to life with a slow, heavy, satisfying pop, 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 a sound of immense and deliberate power. This simple ignition method was its genius. It had no complex high-pressure fuel injectors, no precisely machined injection pumps, and no need for the ultra-refined fuels of its more sophisticated descendants. It could run happily on the cheapest, crudest fuel oil, kerosene, vegetable oil, or even used motor oil. Its low-speed operation, often just a few hundred revolutions per minute, meant less stress and phenomenal longevity. These engines became the rugged hearts of fishing boats, the steady power for remote farms, and the reliable generators for small factories, often running for days or even weeks without stopping. Their downfall was not a lack of strength but a lack of speed. As the 20th century accelerated, the world demanded more power from smaller, faster engines. The true diesel engine, with its high compression and direct fuel injection, was simply more powerful and efficient for its weight. The hot bulb engine, with its necessary warm-up time and leisurely pace, was left behind by progress. Yet its spirit never truly died. In the most isolated places on Earth, in forgotten lighthouse stations and on small farms in developing nations, these iron titans are still found, chugging away faithfully. They are monuments to an era when an engine was built not for peak performance, but for pure, unkillable endurance. The brute force approach to efficiency arrived in the 1980s, cloaked in the brittle promise of advanced ceramics. The vision was the Adiabatic diesel, an engine designed to run hot, so incredibly hot that it would need no cooling system at all. Engineers aimed to line the entire combustion chamber with a ceramic armor, an insulating shell meant to trap the inferno of combustion inside the cylinder where it belonged. This was a direct assault on a fundamental inefficiency of every internal combustion engine, the constant, wasteful dumping of heat into the radiator and the atmosphere. By keeping that blistering energy contained, and then adding a turbocompound system to capture even more power from the still scorching exhaust, this engine promised a quantum leap in thermal efficiency. It was a bold attempt to cheat the Carnot limit, a foundational law of thermodynamics that caps the efficiency of any heat engine. The Adiabatic diesel was not a gentle evolution, it was a full-scale rebellion against physics itself. Yet this rebellion was fought and lost in the microscopic structure of its own armor. The ceramics of that era, for all their technological glamour, were brittle and unforgiving. They could not survive the relentless, brutal cycle of heating and cooling, the dramatic thermal shock that occurs thousands of times per minute inside a working engine. The constant expansion and contraction created microscopic cracks which quickly grew into catastrophic failures. The ceramic liners would shatter, disintegrating into a fine, abrasive dust that would instantly destroy the engine from the inside out. It was a material science war, and the ceramics simply could not hold the line. This forgotten chapter is a stark lesson in the gap between a beautiful concept on paper and the harsh reality of the physical world. The adiabatic diesel was a path that was conceptually sound, a logical and powerful answer to a fundamental problem, but it was a path that led straight into a technological wall, a dream of perfect efficiency shattered by the very materials needed to build it. It remains a ghost of a future that demanded a substance we had not yet learned to create. Some engines were designed not to be opened, but to be sealed away forever. The axial piston engine, often called the barrel engine, is a masterpiece of compact geometry. Picture a cylinder block not standing tall, but lying on its side, with its pistons arranged in a circle like the chambers of a revolver, all pointing directly at the central output shaft they are meant to spin. This entire cylindrical assembly rotates. The pistons do not push a crankshaft up and down. Instead, they press against a fixed, slanted disc known as a swashplate. As the barrel rotates, each piston follows the angled surface of the swashplate, sliding in and out of its cylinder in a smooth, hypnotic dance. This direct conversion of linear motion into rotation is incredibly efficient and compact, creating a power plant that is remarkably dense for its size. For a brief moment in engineering history, this seemed like the perfect answer for cramped engine bays, a cylindrical package of pure power. So why is this brilliant design not under the hood of your car? The swashplate itself was the source of both its elegance and its downfall. The pistons exerted tremendous lateral force against that angled plate, a constant, grinding pressure that created immense friction and wear. Sealing these rotating cylinders against high-pressure combustion gases was a nightmare, requiring tolerances so fine they were nearly impossible to maintain over thousands of hours. Lubricating the complex interface between the piston shoes and the swashplate demanded a perfect and perpetually clean oil film, a condition the real world of dirt and heat rarely allows. This was an engine built for a sterile laboratory, not a dusty back road. Its secret history is not one of failure, but of misapplication. It was an elegant solution that had solved the problem of space, but in doing so, it had created new, more insidious problems of physics and maintenance. The axial engine found its true calling not in the chaotic world of automotive travel, but in the sealed, hydraulic systems of heavy machinery and aircraft, where it could function as a pump or motor in a clean, controlled fluid environment. It serves as a profound reminder that a brilliant design in one context can be a flawed compromise in another, and that the most successful engineering is never about a single perfect idea, but about the careful, practical balance of them all. Cut the crankshaft and you liberate the piston. This is the radical premise of the free piston engine, a design that first emerged in the 1920s. Without a crankshaft to dictate its stroke, the piston assembly is set free, oscillating back and forth between two combustion chambers like a perpetual pendulum of pure force. For decades, this was a tantalizing but unruly concept, a mechanical bronco that was nearly impossible to tame. But today, this old idea has found its perfect partner in modern electronics, resurrecting as the free piston linear generator. In this modern incarnation, the pistons are directly attached to powerful magnets. As they fly back and forth, These magnets travel through a series of coiled wires, inducing an electrical current with every single stroke. The combustion itself directly and instantly creates electricity. This decoupling from rotating parts unlocks extraordinary advantages. The engine can achieve variable compression, finely tuning the squeeze in the cylinder for whatever fuel is available, from gasoline to natural gas or hydrogen. This multi-fuel flexibility is inherent to its design. The potential for efficiency is staggering, as every motion is dedicated solely to generating power, with no parasitic losses to a crankshaft or transmission. The secret history of this engine is not one of a single failure, but of a recurring phantom. Every 20 or 30 years, a new generation of engineers, armed with better materials and smarter digital controllers, rediscovers the free piston's promise. They solve the control problems that stumped their predecessors, only for the technology to once again recede into the background, waiting for the next technological leap. It represents the ultimate modular power unit. Imagine a compact, whisper-quiet box under the floor of your electric car, acting not as the primary motor, but as a range-extending generator that efficiently creates electricity on demand. Or picture one installed in your basement, powering your home with a flexibility and efficiency that our current grid-bound systems cannot match. This is not just an engine, it is a power plant in a box, a ghost from the past that keeps returning with the answer to a future we are only now beginning to build. A perfect sphere of contained fire was the ultimate goal of this engine. In the early 20th century, French inventors Mecox and Petitia created a machine that was as much a geometric proof as a source of power. They arranged its cylinders radially like the meridians on a globe, all converging on a single, central spherical combustion chamber. The very shape was the secret to its promise. This spherical symphony was engineered for perfect, inherent balance. Every force generated by one piston was immediately and gracefully cancelled out by its counterpart on the opposite side of the sphere. The result was an engine that promised to run with an almost supernatural smoothness, a machine that would hum with power rather than shake with violence. It was a mechanical sculpture, a kinetic work of art where form and function were fused into one breathtaking object. But this beauty came at a cost that proved too high. The spherical engine was a nightmare to manufacture. Machining a perfectly spherical central chamber and ensuring the precise alignment of all the radially mounted cylinders required a level of craftsmanship and tolerance that was prohibitively expensive. Every single seal and joint was a unique, complex curve, defying the straightforward, linear production lines that were beginning to dominate industry. It was a masterpiece of aesthetic engineering, a proof that an engine could be a thing of profound geometric harmony. Yet its legacy is that of a brilliant prototype, a stunning demonstration of what was possible when engineers dared to dream in 3 dimensions, even if the world was not yet ready to build their vision. While the solar thermal rocket gently harvested sunlight, another design chose to unleash the very heart of a star. This was the nuclear thermal rocket, and for 2 decades it was not a concept, but a concrete program known as Project Rover. Its operating principle was brutally simple and devastatingly powerful. At its core was a compact nuclear fission reactor, but instead of generating electricity, its only job was to become white-hot. Liquid hydrogen, chilled to near absolute zero, was pumped directly through the reactor's blazing core. In a fraction of a second, this supercold propellant was flash-heated into a screaming, expanding plasma, then blasted out of a traditional rocket nozzle. The efficiency was not just an improvement, it was a revolution. By using the reactor purely as a furnace and not carrying its own oxidizer, a nuclear thermal rocket could achieve nearly double the thrust efficiency, or specific impulse of the best chemical engines. This single advancement meant that a mission to Mars could see its travel time slashed in half, turning a years-long, perilous journey into a voyage of mere months. The engines were real, they were built and they were tested, roaring to life in remote desert facilities, proving that the power for rapid interplanetary travel was already within our grasp. So why are we not using them today? The answer lies not in engineering, but in earthly anxieties. As the Cold War waned, public and political appetite for launching nuclear reactors into space evaporated. The very word nuclear became associated with catastrophe and fallout, a fear that overshadowed the meticulous safety protocols and the sheer potential of the technology. The immense cost of the program was harder to justify in a new political climate, and the vision of a nuclear-powered fleet to the planets was quietly shelved. It remains the most potent propulsion system ever to fire on Earth, a ghost of a future where the solar system felt close enough to touch, grounded not by the limits of physics, but by the weight of our own fears. Some inventors were not satisfied with simply rethinking the engine. They sought to overturn the very laws of the universe itself. Throughout the 20th century, a peculiar breed of machine would occasionally surface, claiming to achieve the impossible, a reactionless drive. These devices, often called gyroscopic propulsion engines, were built around a simple, spinning gyroscope. Their creators, earnest and passionate, would demonstrate a curious phenomenon, a slow, creeping motion across a table as the gyroscopes inside whirred and precessed. They claimed this was net thrust, a genuine forward force generated without pushing anything backward, a clear violation of Newton's third law. For every action there is an equal and opposite reaction. It was the ultimate free lunch, a way to propel a car, a ship, or a spacecraft without any fuel or exhaust. The secret history of these machines is not one of hidden technology, but a profound lesson in human psychology and the subtle pitfalls of experimentation. In every single case, without exception, the measured thrust was traced to something mundane, an overlooked interaction with the environment. Sometimes it was a subtle vibration transferring momentum through the floor. Other times it was a weak magnetic field interacting with the Earth, or a thermal current from the engine's own heat creating a tiny buoyancy effect. The inventors were not usually frauds. They were often brilliant tinkerers who had fallen victim to a powerful self-deception, their deep desire for a breakthrough blinding them to the mundane reality of their measurements. These phantom engines represent a frontier not of engineering, but of belief. They live in the gray area where the line between visionary and crank becomes dangerously blurred, where a beautiful idea is so compelling that it overpowers contradictory evidence. They serve as a crucial reminder that the laws of physics are a harsh but utterly impartial judge, and that the most difficult force to overcome in any experiment is not gravity or friction, but the overwhelming power of our own hopes. Fire could burn without heat. This was the strange promise of catalytic combustion, a forgotten path where engines would work not with a roar, but with a quiet chemical sigh. Imagine a metal surface, a catalyst, that could coax fuel and air into combining at temperatures barely above room temperature. There would be no brilliant flame, no searing blast of heat, just a gentle, immediate release of energy. This cool combustion was the ultimate engineering dream. It promised to completely eliminate nitrogen oxide pollutants, which are only born in the fierce heat of a traditional fire. It would also conquer thermal loss, that great thief of efficiency, because the engine itself would never get hot enough to waste energy radiating into its surroundings. The exhaust from such a machine might even be clean enough to breathe. Visions emerged of whisper-quiet generators for homes and libraries, or car engines that produced little more than warm water vapor and carbon dioxide. The blueprints for this silent revolution are not in secret vaults, but scattered and forgotten in academic journals and obscure patents from decades past, a field of research that simply faded away. The core problem was one of delicate control. A catalyst is a finicky artist. Trace impurities in the fuel, like sulfur, would permanently poison its active sites, coating the surface in a layer that rendered it useless. Even with a perfect fuel, the reaction rates were often too slow to produce the rapid power pulses an engine needs, and starting the process was one thing, stopping it was another. How do you precisely throttle a chemical reaction that wants to spread across a vast surface area all at once? It was like trying to control a phantom, a reaction that was either too lazy to begin or, once started, impossible to contain without quenching it entirely. This ghost of an engine remains one of the most elegant what-ifs, a future where the very idea of combustion was transformed from a violent explosion into a gentle, controlled handshake between molecules. The quietest engine of all might be one that harnesses a river's gentle farewell to the land. Where fresh water flows into the sea, a tremendous, invisible force is born from the simple difference in saltiness. An osmotic engine taps directly into this natural tension, a machine that treats the meeting of two waters as its fuel. It works by exploiting a fundamental desperation of nature, the drive toward equilibrium. Imagine a chamber divided by a special, semi-permeable membrane. On one side, you have fresh river water, on the other, the dense brine of the ocean. The fresh water, seeking to dilute the salt water, is compelled to rush through the membrane into the saline chamber. This massive, one-way flow of water creates a powerful pressure spike on the salt water side, a head of steam that can be used to spin a turbine and generate electricity. It is a process with no combustion, no moving parts in its core principle, and no emissions beyond the slow, natural mixing of the estuary itself. The concept is centuries old, a ghost of an idea whispering from the notebooks of natural philosophers who understood the raw power latent in the world's great deltas. So why are our rivers and oceans not lined with these silent power plants? The dream of osmotic power has been repeatedly dashed on two cruel, practical realities. The first is the membrane itself, the very heart of the engine. It is fantastically delicate and it fouls almost instantly. Microscopic organisms, silt, and organic debris in the water cling to its surface, clogging its pores and strangling the flow in a matter of hours. Keeping it clean requires a constant, energy-intensive process of scrubbing and backflushing that can consume more power than the engine produces. The second, more fundamental issue is power density. The pressure generated is immense, but the volume of water moving through a practical-sized membrane is frustratingly small. To power a single city block would require a membrane array the size of a football field, a vast, expensive, and fragile surface constantly at war with the sea. This engine represents a path of profound philosophical contrast. It is not about conquering nature with violent explosions and extreme heat, but about subtly leveraging its existing, gentle gradients. It is a machine of patience, of working with the slow, persistent rhythms of the planet. Its continued obscurity is a poignant reminder that the most elegant energy source is not always the most practical one, and that some of the most peaceful power in the world remains just beyond our grasp. Even the wasted shudders of a machine can be put to work. This is the philosophy behind piezoelectric power, a way of harvesting energy not from fuel, but from vibration and stress itself. While not a primary engine in the traditional sense, the piezoelectric generator represents a radical shift in thinking about what constitutes a power source. Certain crystals and ceramics possess a unique property. They generate a small electrical voltage when you squeeze them, bend them, or subject them to mechanical pressure. It is a direct conversion of physical force into electricity, with no combustion and no moving parts beyond the material's own microscopic flex. The secret history of this idea is not one of a single breakthrough, but of a quiet, persistent quest for efficiency, a philosophy of wasting nothing. Think of an engine where the very vibrations and pressure pulses of its own operation, the very noises and shakes we normally try to dampen and eliminate, are captured. Piezoelectric elements could be embedded in the engine mount, lining the intake manifold, or even placed within the cylinder head. Every shudder, every acoustic pulse, every minor flex in the metal would then generate a tiny trickle of electricity. This harvested power could run the engine's own brain, its sensors and control units, creating a system that partly powers itself from its own perceived waste. This is parasitic energy harvesting in its most elegant form, making a virtue out of a vice. You can find this principle already at work in the world around you. Some modern dance floors use piezoelectric tiles to capture the energy of footsteps, powering the lights above. The push-button ignitor on a gas grill uses a spring-loaded piezoelectric crystal to create the spark that lights the burner. This is a technology of incremental gains, where small amounts of scavenged energy add up to a meaningful whole. It asks a profound question of our engineering philosophy. Why design a machine to merely tolerate its own weaknesses when you can design it to feed on them? This path leads toward a future of hyper-efficient systems, where the distinction between a machine's operation and its power supply begins to beautifully blur. A single drop of water skitters and screams across a scorching hot pan, dancing on a cushion of its own creation. This is the Leidenfrost effect, a mesmerizing physics trick known to every chef. Yet hidden within that tiny, frantic dance is the blueprint for an engine. By etching a surface with microscopic, ratchet-like teeth, engineers discovered they could channel the chaos. The vapor cushion no longer forms symmetrically. It pushes harder in one direction than the other, creating a tiny but undeniable force. That droplet of water is no longer just dancing. It is being systematically propelled, turned into a piston for a motor you can barely see. The secret history of the Leidenfrost engine is a journey from parlor trick to propulsion principle, a testament to the power of looking closer. It reveals how the most mundane phenomena, the simple act of a liquid meeting a hot surface, can be sculpted into directed motion with nothing more than clever geometry. This is not an engine built with pistons and gears, but with texture and tension. It is a machine where the very substance being heated becomes its own moving part, a closed loop of energy conversion happening on a scale almost too small to comprehend. What other invisible forces are at work in our everyday world, just waiting for the right pattern to set them into motion? Metal holds a hidden memory, a ghost of a shape imprinted upon its very atoms. This is the strange world of shape memory alloys, metals that can be bent and twisted, yet will snap back to their original form with nothing more than a gentle application of heat. This simple property became the heart of one of the quietest and most peculiar engines ever conceived. Imagine a simple wheel with wires made of this special metal, like nitinol, stretched between its hub and its rim. You would not need pistons, cranks, or explosions. You would only need two basins of water, one warm and one cool. As each wire dips into the warm bath, it remembers its shorter, contracted length and suddenly shrinks, pulling on the rim of the wheel. This contraction gives the wheel a small turn. As that same wire rotates into the cool bath, it becomes pliable again, easily stretched back to its longer form by the opposing pull of other wires, ready to repeat the cycle. The wheel turns in a slow, silent, hypnotic rhythm, powered by nothing but a temperature difference. Its operation is a form of mechanical magic, an engine built from a material that is also its own motor. So why is this elegant, silent machine not powering our world? The secret history of the shape memory alloy engine is a story of profound patience meeting impractical limits. Its fatal flaw was an efficiency so low it bordered on the philosophical. Almost all the heat energy poured into the system is wasted, lost to the surrounding water and air, with only a tiny fraction converted into actual motion. You could run one of these engines for hours on the heat from a cup of coffee, and it would barely generate enough power to lift a feather. It is an engine that demonstrates a principle more than it delivers usable work. Yet, this very inefficiency points toward a radically different philosophy of power. This is a materials-centric approach, where the intelligence of the engine is baked directly into the substance itself. The metal is not just a component, it is the actuator, the spring, and the piston all in one. It asks us to consider a future where our machines are not assembled from countless parts, but grown or printed as single, intelligent materials that respond directly to their environment. Where could such a patient, silent technology find its purpose? Perhaps in environments where any vibration is a catastrophe, or where waste heat is abundant and free. The shape memory alloy engine is less a failed invention and more a whisper from an alternate path, a demonstration that sometimes the most profound ideas arrive not with a roar, but with the soft, persistent click of a metal remembering itself. A wine glass shatters from a single, pure note, its crystal structure undone by vibrations we cannot even see. This is the raw, untamed power of resonance, a force that some engineers sought to harness not for destruction, but for creation. They envisioned resonant acoustic engines, machines where entire chambers became gigantic amplifiers, turning whispers of sound into a tidal wave of usable force. These were not the subtle, part-less hum of thermoacoustic devices, but muscular macro-scale engines designed for industrial labor. Their core principle was the standing wave, a sound wave trapped and perfectly reinforced within a carefully shaped cavity, its peaks and troughs held motionless in space, vibrating with immense energy. In one of these resonant chambers, the very air itself becomes a powerful, invisible piston. Picture a giant tube sealed at both ends, with a speaker at one side emitting a specific, precise frequency. When the pitch is just right, the sound wave reflects back and forth, building upon itself until the pressure swings inside are massive. At the pressure peaks, you have zones of intense compression, and at the nodes, points of near vacuum. This creates a powerful, rhythmic push and pull that can be used to drive a piston, oscillate a diaphragm, or even pump a liquid directly, all without any physical connection to the moving parts. The secret history of these engines is a saga of controlled chaos, a high-wire act of balancing incredible power with the constant threat of self-destruction. Taming a standing wave of that magnitude is like trying to hold a lightning bolt in a bottle. The acoustic forces involved are so strong they can fatigue and crack metal, and the slightest miscalculation in the chamber's geometry or the driving frequency can cause the entire system to shake itself apart. It is engineering at the edge of instability, where the same physics that makes a bridge collapse in the wind is carefully coaxed into pumping water or generating electricity. Why did this path of acoustic leverage not redefine our factories? The challenge was one of refinement and application. While brilliantly powerful for specific, resonant tasks, these engines were not versatile universal power sources. They excelled at a single, rhythmic job but struggled with the variable speeds and changing loads demanded by most industrial processes. They were masters of one trade in a world that demanded jacks of all trades. Yet the ghost of this idea persists wherever extreme conditions meet simple needs. Imagine a natural gas pipeline stretching for miles with a small but constant pressure differential. A resonant acoustic engine could be tuned to that specific flow, using the energy of the gas itself to create a standing wave that powers monitoring equipment forever with no external fuel. This is a future where our infrastructure hums with a quiet, self-sustaining power, a symphony of resonance doing the work of an engine. Gravity itself has always been the ultimate siren's call for inventors. No other force is so constant, so universally present, and so tantalizingly powerful. For centuries, this pull toward the Earth's center has inspired a specific kind of madness, a glorious and heartbreaking pursuit of the gravity engine. These were not machines that converted heat or chemical energy, but devices that claimed to outwit physics itself, creating motion from a clever arrangement of weights and levers that would, in theory, run forever. Classic design was the overbalanced wheel, a circle with rolling balls or swinging arms on hinged levers. The idea was beautifully simple. On one side of the wheel, the weights would be extended far from the center, creating a longer lever arm and more turning force. On the other side, they would fold in close to the hub, offering less resistance. The wheel, perpetually unbalanced, would then turn forever, lifting its own weights and performing useful work along the way. It was a vision of a closed loop, a machine that fed itself. The secret history of these devices is a graveyard of broken dreams and bankrupted fortunes. Charismatic inventors would demonstrate intricate, beautifully crafted models that seemed to turn on their own, captivating wealthy backers and the public alike. They promised a world liberated from toil, from fuel costs, from the very limits of resource scarcity. Yet, every single one of these machines, without exception, eventually stopped. Some had hidden clockwork mechanisms wound up before the demonstration. Others relied on cleverly concealed magnets or subtle tricks of air currents. The fundamental flaw was always the same: friction. Every pivot, every rolling surface, every bearing slowly bled away the tiny, imaginary surplus of energy the inventor believed they had created. The dream of perpetual motion was not a failure of imagination, but a refusal to accept a fundamental conversation the universe is always having, a conversation where every action has a cost. These inventors were trying to build a system that only listened but never spoke, that took energy but never gave anything back. So why do we still remember these failures? They represent an undying human curiosity, a drive to challenge the impossible even when the laws of physics stand like an unbreakable wall. They are the ghosts at the feast of engineering progress, a constant, humbling reminder of the line between visionary ambition and futile obsession. Their legacy is not a working machine, but a philosophical question: how far should we push against the immutable rules of reality? And in that endless pushing, even in failure, do we sometimes discover something else entirely, a new principle or a deeper understanding we would have otherwise missed?